Okay, everything we've been doing so far in this unit has led up to this important video. It's called Coupled Reactions, and it goes back to this question about how do we make a reaction go forward if its favorability is uphill. Let's take, for example, this glucose plus phosphate to glucose 6-phosphate reaction we talked about before. This is an uphill reaction. It doesn't mean it can't go forward, it just means it has a propensity not to. And that's because its delta G naught prime is uphill. It's positive. It's plus 14 kilojoules per mole. Now, we already talked about one way we can make this reaction go forward. If we increase substrates or decrease products, then Le Chatelier's principle tells us we can move that forward. So, let me tell you that when we consume any food that contains glucose, the very first thing we need to do is put a phosphate on the 6th position, but that's a hard thing to do. And we could increase glucose and phosphate, but what if we don't want to wait for that? What if we don't have a lot of glucose in our diet? We still want to get it phosphorylated. It turns out there's another way to make this happen, and in fact, it's the way that we do it in our body. Now, as we move on and go to the page following this one, we have to understand that this page is critical because it tells us the different types of high energy linkages that are going to be involved with coupled reactions, and it tells us their energy. Let me just remind you that when we break these high energy linkages, we end up with negative delta G naught primes. Whenever you hydrolyze a linkage, it's always favorable and downhill. When we go backwards, it's always uphill, and the same number, but the sign reverses to positive. Okay, let's go on finally to the next page and tell you about coupled reactions. As we said before, we have these two reactions, and what we did is assign them delta G naught primes. Now, we can look at each one of these and recognize that when we hydrolyze ATP to ADP and phosphate, we have a negative 30 kilojoules per mole. That's an approximate value based on what we know happens when you hydrolyze a phosphoanhydride. This is negative 30. It's favorable. When we take glucose plus phosphate to make glucose 6-phosphate, we end up abstracting a water, and we said that this is positive 14. Let's just call it positive 15 kilojoules per mole because that's sort of the general value we have for phosphoesters. Now here's the deal. If we do these things together on one enzyme, we can add them all up and have a coupled reaction. What do we mean by that? Well, we can add up the chemistry side of things, and just like with mathematical equations, we can cross out things that are on both sides. Take a moment and find things that are on both sides, the reactant and product side, and cross them out. I'll give you 30 or 45 seconds to do that. Pause, and then add everything up on each side, and let's lay out what is left down here for substrates and products. Okay, when we cross things out that are on both sides, we can cross out water and we can cross out phosphate. And what we're left with is a coupled reaction in which ATP and glucose come together on one enzyme, and we end up transferring a phosphate from ATP to the glucose to make ADP and glucose 6-phosphate. Now, that is an actual reaction. It's the first reaction of glycolysis that we're going to learn about in the next chapter, and it really happens this way. What's more important is that we can add up the delta G naught prime values for the half reactions, and we end up with negative 15 kilojoules per mole. So it's as simple as what you have before you. If we can take two half reactions, one that is favorable and one that is unfavorable, and combine them together in one reaction, one enzyme, we end up having an overall favorable reaction. That's it. Let me tell you two things to sew this video up. First of all, what we need to point out is that this is a half reaction right here. And this is a half reaction. And this is a full reaction. The way we think about this is that the full reaction is actually what is happening in reality. The half reactions are just accounting. It allows us to split it into two parts and split the energy into two parts and determine what's happening here. Now, the second thing I want to tell you is there is a nice way to summarize these things, because often what we're going to do is look not at half reactions to make a full reaction, but we're going to start with a full reaction and try to parse it apart into half reactions. How do you do that? The answer is you're always going to ask yourself two questions. What are you breaking? And what are you making? If you can remember to answer these two questions, and you can do so appropriately by recognizing the right high energy linkages, then you can really never go wrong with these types of questions. So how would we answer this one? What are you breaking? We're breaking a phosphoanhydride. And what are you making? We're making a phosphoester. And this can be summarized by saying that the breaking of a phosphoanhydride drives the formation of a phosphoester. This is a coupled reaction. We're going to practice it a lot on the homework. It's a challenging skill because you've got to combine recognizing the high energy linkages with this kind of mathematical approach to adding half reactions together. We'll give it a try on the homework.